Our first example of a familiar conservative force is gravity. So let's consider the force of gravity acting on an object that's moving around near the surface of the Earth, where we know that the force of gravity will be constant. So here I've got this little orange box that's moving around. Let's say X is the horizontal direction, Y is the vertical direction. And the box moves along some path, moves up for a bit and then over, around and around, and ends up over here sometime later. So it has an initial position and a final position. Gravity will meet the force of gravity that acts on the block over the course of this path. It meets our conditions for a conservative force because that force of gravity on the block doesn't depend on how the block is moving. It doesn't depend on any other interactions the block is having, and it doesn't depend on the history of the block either. That force of gravity is a function of position only in the sense that it is a constant. And a constant function is still, after all, a function. So gravity is a conservative force for us. It's just a constant. It's the same exact value at all points along that path. So if we compute the work done by the force of gravity on this object as it moves from its initial position to its final position, we get this. Work done by gravity, we integrate Fg dot dr along that path. And note that, let's see here, our dot product can be expanded to write our work integral as the sum of these work integrals. Gravity has no x component and no z component here, only the y component, so it simplifies down to Fgy dy along the path. And the y component, the vertical component of gravity, is minus mg. This is minus mg times j hat there. So minus mg is our y component. That's a constant, so we can pull it out of our integral, and we're left with the integral of dy over that path, adding up all the little changes in the y direction, all the little vertical displacements, gets us the overall or big vertical displacement delta y. So there's our expression for the work done by gravity minus mg delta y. And notice, it only depends on the final y coordinate and the initial y coordinate, y2 and y1. It does not depend on any other properties of this path, how long this path was or how curvy or twisted or convoluted it was. All that matters are the final and initial y coordinates, indicating to us that the work done by gravity is what we call path independent. The work done on an object by gravity depends only on where it started and where it ended, not the path in between. So for instance, I could get the block from here to there along some other path. I could have had it go like that instead, and gravity would have done the exact same amount of work along the pink path as it did along the black path, because they have the same starting and ending points. The work done by gravity is path independent. And we'll see that this is a general property of conservative forces. The work that they do is always path independent. Secondly, the work done by gravity also does not depend on our choice of reference point. I have a set of xy axes here with an origin located there. The origin is our reference point, RP. I could have picked a different set of axes. I could have, say, put a reference point and origin way up there and had these axes. I'll call them y prime and x prime with a 0 there, so some different reference point. So I could have said that y equals 0 up here rather than y equaling 0 down here. And so in this case, along these axes, this would be the initial y coordinate of the box, and this would be the final y coordinate of the box. Note that these y coordinates would be negative since they're below this reference point, as opposed to these y coordinates over here, which are positive above that reference point. But even by changing my reference point, and even by putting it way up here, note that the change in y, the delta y, is still the same. This final y minus this final y, minus this initial y, is the same value as this final y minus this initial y. Changing the reference point changes the y values, but it doesn't change delta y. And if it doesn't change delta y, then it doesn't change the work done by gravity. So I'm arguing that not only is the work done by gravity path independent, it's also independent of your choice of reference point. You are free to set y equals 0 down here, or up here, or anywhere you want, and that choice will not affect the work that's done by gravity. Basically, you have a freedom to choose a reference point. It doesn't alter the physics. It's the change in y that matters for the physics, and your choice of reference point doesn't impact the change in y. Okay, I'll make some more points about conservative forces here using gravity as an example. For any conservative force, we can define a corresponding potential energy function. For instance, here with gravity, the work done by gravity is given by this expression here, which is minus mg times final y value minus initial y value. And if I distribute that mg across these terms, I get the opposite of mgy2 minus mgy1. So apparently, the work done by gravity along some path is equal to the opposite of the change in mgy, final value of mgy minus initial value of mgy. So I'm going to call this quantity mgy. I'm going to define that to be the gravitational potential energy, Ug. So this is minus the final value of Ug minus the initial value of Ug. So we have here the work done by gravity on an object along some path is equal to the opposite of the change of this corresponding potential energy function, gravitational potential energy, Ug, where Ug is a function of position equal to mgy. That three-line equal sign means is defined as. Ug is defined as mgy. And it is a function of position only because our force was a function of position. This will be another general property of conservative forces. We can define for each conservative force a corresponding potential energy function that's a function of position only. An energy that depends just on where you are. Does not depend on how you're moving or other forces or your history. Depends only on where you are. And we say that UGY equal to the mass of the object times little g times its y coordinate relative to some reference point that you get to pick. UGY is the gravitational potential energy of the mass plus Earth system. This is an important point. It is the interaction between our little mass, our little block here, little orange block, and the entire planet Earth. It's the interaction between them that the force of gravity represents. So it's the interaction between them that creates this potential energy. So if I put our little block and the entire Earth into a system, we say that the total mechanical energy of the mass plus Earth system. Now I know I'm getting a bit ahead of things here because we haven't really introduced total mechanical energy yet, but we will soon. The total mechanical energy of this system includes the kinetic energy of this little mass if it's moving around, the kinetic energy of the whole planet Earth if the whole Earth is moving. So each of these individual objects could have some kinetic energy. But it's the combination of the pair of them that possesses the potential energy. It's the system that has potential energy. One object by itself cannot have potential energy. So if it's just the mass here, the mass can have kinetic, but there would be no kinetic for the other objects and no potential energy. It's only when we include both objects that potential energy appears. So one term here, one Ug term for the potential energy of the system, while we have separate kinetic energy terms, one for each object in the system. All right, we've hit on several key properties of the force of gravity, which we will see are general properties of conservative forces, this, and the existence of a potential energy function, given here. I want to make two more points about the sign, two comments on signs, positive and negative signs in gravitational potential energy. Note that UG, as we've defined it, can be positive, negative, or zero. And that sign can depend on your reference point. So if we define UG like this, since Y can be positive, negative, or zero, UG can be positive, negative, or zero. In contrast to kinetic energy, 1/2 mv squared, which is always positive or zero. Always positive, but UG can be negative, and that's okay. To help illustrate that point about sign, suppose I've got a black set of axes here, coordinate axes here, with a reference point. And here's a mass, this little orange mass here, sitting at a coordinate y1. Note that y1 is below 0, so y1 would be negative. So the gravitational potential energy of the mass, well, the mass Earth system, the gravitational potential energy would be UG equals mg times y1, and since y1 is negative, UG would be negative. So according to this reference frame in black, this mass has negative gravitational potential energy. But I could have picked a different reference point. I could have put my reference point over here, said y equals 0 way down here instead, and drawn these blue axes, y prime and x prime. And the y coordinate of the block relative to this reference point is this positive value, y prime 1. And since y prime is positive, then UG prime, the gravitational potential energy measured by this frame, would be positive. So not only can UG be negative, but the sign of UG depends on where you put your reference point. This person's reference point, according to them, the mass has negative gravitational potential energy. According to this person's reference frame, the mass Earth system has positive gravitational potential energy. And that's okay. That's okay because what really matters is the work that gravity does and the changes in energy. The work that's done by the force of gravity equals to the opposite of the change in UG equals minus mg delta y in the black reference frame. But any change in y according to the black reference frame is equal to the change in y in the blue reference frame. They will both agree on the change in y. The point I made back here. Even though you have different reference points, both reference frames will measure the same delta y. That'll be the same to both of them. So since they both have the same delta y, then they both have the same change in gravitational potential energy. They both have the same work done by gravity. So we are free to choose these different reference frames since the physics that matters is the physics of energy transfer, and the energy transfer will be equal in both frames. Okay, so nothing wrong with negative UG. Although you may wonder about the negative sign in this equation here, in the minus delta UG. I mean, you saw how I derived it, so you saw where it came from, but what does it mean? How do we interpret the negative sign there? Let me make an argument. According to our work energy theorem, if the force of gravity does positive work, like for instance, if the force of gravity, which we know is down, acts on an object that's moving with a velocity that makes an angle less than 90 degrees with it, so they're relatively supporting one another, then gravity would be doing positive work on this object as it moves down, and that object would be speeding up. The kinetic energy would increase. So if force of gravity does positive work, kinetic energy increases. We'll soon be discussing conservation of energy, but you're already basically familiar with the idea. You know that if kinetic energy increases, it can't have come from nowhere. We can't just create kinetic energy out of nothing. If kinetic energy increases, it must be at the expense of gravitational potential energy. The UG must decrease if K increases. In other words, we're converting potential energy into kinetic energy if K is increasing. So here in this situation, if the force of gravity does positive work, K is increasing, UG must be decreasing. Therefore, if the work done by gravity is positive, then the change in UG must be negative, and vice versa. That's what that sign here is telling us. If this is positive, then the change in UG must be negative. Here's a picture illustrating that same point. If I got this block moving upwards, its gravitational potential energy is increasing, but since the force of gravity is down, gravity will be doing negative work. So gravity is doing negative work as this block increases in gravitational potential energy. So the WG and the UG and the delta UG have opposite signs. Likewise, if the block is moving downwards, gravity is doing positive work, but the UG is decreasing, so delta UG is negative, and the work done by gravity is positive.